For 10 years, the United States government put a deliberate error into the GPS signal, not a bug, a designed lie broadcast from orbit, so the system would tell you the wrong place on purpose. The first car navigators had it, every civilian receiver had it, and then one morning in the year 2000, somebody switched it off. This is the story of why they built it and why the whole thing started with a submarine that could not find itself. 3 things had to go wrong before any of that could go right. A signal 2 men listened to because nobody had told them to, a question asked backwards, and a system declared a failure before it worked. Start with the signal. 3 days after the Soviet Union put a transmitter in orbit in a cafeteria at the Applied Physics Laboratory in Maryland, 2 junior physicists, William Geyer and George Weifenbach, are arguing about a beep. Nobody assigned them this. It is not a funded program. It is not anyone's job. And the computer time it will take is not theirs to spend. By late afternoon, they have borrowed a receiver and found the signal. That evening, they come back and lay the national time signal down the same track. So every second of tape carries its own timestamp, and there it is, a tone sliding downward as the satellite crosses the sky, something circling the planet every 96 minutes. They can hear where it is. In 5 months, one question about that falling tone will turn the whole thing inside out. If the sound tells you where the satellite is, can it tell the satellite where you are? Welcome to From Smoke to Signal. I'm Mo, and SmartCat and I are here to prove one thing. Every signal has a story. Let's begin. This is a story about a piece of arithmetic run backwards. Find the satellite from a place you know, then turn it around and find the place from a satellite you know. That inversion is the whole idea, and it was built for a very specific customer. A submarine that could not afford to be lost. And it is worth being exact about that customer because the whole story is downstream of her problem. A missile submarine goes under and stays under. On the first deterrent patrol, 66 days without surfacing. She cannot take a star sight through 400 feet of ocean, so she navigates by dead reckoning, speed, heading, time, and an error that grows every hour she stays down. Now put 16 nuclear missiles aboard. A missile knows where it is going relative to where it started, so every meter of uncertainty in the boat's position is a meter of uncertainty at the target. She is the most powerful thing in the ocean, and she does not reliably know where she is.
So you're telling me the trick is doing the math backwards, that's it? No new physics, no secret formula, just turning the same equation around and reading it the other way.
Sputnik went up on a Friday, October the 4th, 1957. By their own recollection, nobody at the Applied Physics Laboratory came in that weekend to try to receive it. The following Monday, October the 7th, 3 days after launch, 2 physicists, William Geyer and George Weifenbach, were eating lunch in the APL cafeteria when the conversation turned to the beeping metal sphere everyone was talking about. Nobody assigned them this. It wasn't a funded program, and it wasn't anyone's job, in their own words, years later. It was not organized. We all just did it. That same afternoon, on their own time, they went looking for the signal.
Unpaid, unauthorized, running purely on lunch break enthusiasm. Somehow that's still more initiative than my last performance review.
The equipment was whatever was already sitting in the building. Weifenbach had a good 20 megacycles receiver. Megacycles in the language of the day, left over from his doctoral work in microwave spectroscopy, where it had served as a frequency reference. Gear had just bought himself a hi-fi tape recorder. Between them, that was the whole kit. They laid the National Bureau of Standards time signal, broadcast from station WWV, onto that same audio track, so every second of tape carried its own timestamp. And in 1957, the station wasn't out in Colorado yet. It was 12 miles up the road in Maryland. And the antenna pulling this in was a 2-foot piece of wire hanging off the back of the receiver. No dish, no steerable array, nothing that had to track anything across the sky. At the time, it was simply what was handy. It would turn out to be the most important fact about the entire method, because the customer nobody had thought of yet was a submarine, and a submarine cannot raise a steerable dish. In the receiver, it all arrived as sound, and there's a reason it was audible at all. The Soviets had deliberately set Sputnik's transmitter about 1,000 cycles off an exact 20 megacycles, so any receiver on Earth tuned to 20 would produce a tone instead of silence. They wanted the world to hear it, and the world did, a pitch sliding from roughly 1,500 cycles down to about 500 across a single pass, never quite reaching zero, audible start to finish. What Moscow cannot have intended was that the same decision handed two Americans a clean, continuous measurement of their satellite's motion. That evening, they came back after dinner and started recording complete passes, horizon to horizon.
Wait, back up. They had the signal by dinner that Monday. So they had the orbit too. That same week.
Not even close. And this is the single most common mistake in the popular version of this story. Getting the signal took an afternoon. Getting the orbit took the better part of 5 months. For those first weeks, there was no computer near this problem. They reduced the early passes by hand, graphically, plotting the curve on paper. And for a first guess at the satellite's tilt, they leaned on inclination estimates they read in the newspapers that autumn, same as anyone following along at home. 3 things had to be separated out of that one curve before an orbit could fall out of it. A correction for how the ionosphere bends the signal coming down, a correction for drift in the satellite's own transmitter, and underneath both, a least squares inversion, the arithmetic that turns a curve into an orbit. Miss one and the answer is wrong. Now, the computer. Everybody knows the shape of this part. 2 physicists, a mainframe, the numbers come out. Hold that picture. Sputnik's transmitter died on the 26th of October, 1957. Batteries flat, beeping over. Only after that did the lab's director, Ralph Gibson, release funds for time on APL's newly acquired mainframe, a machine the 2 of them remembered as a Univac 1200F. The computer didn't crack this. It arrived after the data ran out to see how good an answer they could squeeze from what they already had. And here's the part that's luck as much as genius. In their own words, every organization in America, Europe, and the Soviet Union chartered to track satellites had chosen angle measurements, interferometers, a baseline, and array across multiple stations. The Naval Research Laboratory alone had a whole field of antennas for it. These 2 had 1 wire, 1 building, 1 pass. They weren't being contrarian. Doppler was the only data they had.
Wait. Everyone else had angles and a whole array. These 2 had a tape recorder. Why did they get it? Not the guys with the actual equipment.
Here's what one tone can tell you. A pitch rises as something comes toward you and falls as it goes away. As the satellite closes, the shift is high. At closest approach, it crosses through 0, then it goes negative as the satellite recedes. How steep that fall is tells you how close the pass was. The moment it crosses tells you when, and so where, it passed overhead. Slope for distance, timing for position. That's the trick. What they proved was that a whole orbit could come out of that single curve in no baseline, no second station, no array. It took the entire curve nearly horizon to horizon and all 3 corrections. But it did not make them first to know where Sputnik was. Astronomers at the University of Illinois had eyes on it the night it launched, computed its elements on the iliac, and published in Nature by the 9th of November. From optical sightings, angle data, the orthodox way. What Geyer and Weifenbach claimed was narrower and stranger. By their account, they were the only ones anywhere analyzing Doppler data for this at all. Not the best at it, the only ones trying. And here's why that wire mattered. When the Navy went looking for a way to fix a submerged submarine's position, Geyer and Weifenbach counted exactly 2 other candidates. 1, active sonar imaging of the ocean floor, a ballistic missile submarine shouting into the water, the one thing it exists never to do. 2, a naval observatory plan for a 3-foot dish on a stabilized platform taking direction measurements, a beautiful radar target riding on the boat that must not be seen. Doppler needed 1 piece of wire that never had to move and never had to transmit. The limitation was the qualification.
So the cheapest thing in the room won because it was the only one that could keep its mouth shut. Finally, a professional skill I actually have.
On Monday, March the 17th, 1958, Frank McClure called Geyer and Weifenbach into his office and asked them to shut the door. McClure headed APL's research center, a physical chemist, not a radio man himself, and he had one question: could they run their arithmetic backwards? We know this happened because McClure put it in writing. The next day, he sent 2 memoranda to APL's director, Ralph Gibson, dated the 18th of March, writing that their work provided a basis for a relatively simple and perhaps quite accurate navigation system. His second memo named the customer outright the Navy's Special Projects Office, not a legend remembered decades later, dated correspondence.
2 memos and a closed door. Somewhere a superpower just launched a satellite, and all he's got is interoffice mail.
Here's the crux. Solving for the satellite's orbit meant 9 unknowns, 6 orbital elements, 3 system parameters. Flip it, And solving for the ground station instead meant 5, 2 coordinates, 3 system parameters. Add a cooperative satellite broadcasting 2 frequencies and it dropped to 3, same data, far fewer things you don't know. And McClure wasn't being idly curious. He'd been spending part of his time downtown in the Navy office responsible for Polaris, the ballistic missile they were about to put under the ocean. He knew it from the inside, and he knew what it needed, a launch position at sea, known, ideally, to within a few hundred feet. Fire control had to know where the boat was to put a warhead on a target. That requirement paid for the whole program. 17 days later, the 4th of April, 1958, Ralph Gibson sent a 50-page proposal to the chief of the Bureau of Ordnance, and APL published exactly what it promised. A completely passive user, the submarine transmits nothing because the whole point of a submarine is that no one can find it. 1 antenna, no baseline, satellites of about 50 pounds, circular errors estimated at roughly half a mile, and by APL's own account of the document, a first phase price of $937,000.
$937,000 in 1958 to track a boat that isn't allowed to say where it is.
McClure didn't build this alone. Within days, he brought in Dick Kirshner, who stood up APL's new space department that same year. McClure conceived the idea. Kirshner turned it into hardware that actually flew. And now, the tidy version of what happens next. Brilliant idea, grateful Navy, blank check. That's how these stories are supposed to go. It isn't what happened. Polaris money carried the project through the summer of 1958 on borrowed time. Then in October, ARPA, the Pentagon's new research agency, sponsored it, authorizing APL to build satellites and ground stations. And by APL's own history, that happened partly because the Navy was reluctant to admit out loud that it had a navigation problem at all.
The customer didn't even want it. Somewhere a defense contractor just felt a chill.
So ARPA asked an outside review board a blunt question, well, how long would one of these satellites actually last? Going on the electronics of the day, the estimate that came back was about 2 weeks. Transit satellites went on to average more than 14 years in orbit. 2 of them ran past 20.
They budgeted for 2 weeks and got 2 decades. Somebody owes that estimator an apology or a raise.
And the version you'll usually hear runs straight from the idea to the working system as though the hardware simply obeyed. Here's the actual ladder. Transit 1A, the first launch attempt, went up from Cape Canaveral on September 17th, 1959, and never reached orbit. Transit 1B followed on April 13th, 1960, first to actually orbit, running 89 days, but experimental, a proof of technique, not a service. The satellite the Navy could operate for real fixes was Transit 5BN2, December 5th, 1963. Remember that date. You already know this feeling. Drive into a tunnel and the blue dot on your dashboard doesn't stop. It keeps crawling forward on your last known speed and heading because there's no signal left to check it against. That's dead reckoning. Pure integration of your own motion with nothing outside correcting it. And the error compounds. The longer you go without a fix, the further that guess drifts from where you actually are. In a tunnel, maybe 90 seconds of it. Now put that same guess under 600 feet of ocean for 60 days.
Wait, if my phone loses the plot for 90 seconds in a tunnel, how does something the size of an apartment building keep a straight face about knowing exactly where it is, underwater, for 2 straight months?
A submerged submarine has no view of the outside world, no stars, no horizon, nothing coming in. Its inertial navigator integrates every turn and every change in speed into a running position. But the sensors doing that math are never perfect. Small errors accumulate, and the longer the boat runs blind, the further its believed position drifts from the true one. For a boat carrying nuclear missiles, that drift is the whole problem. If you don't know where you're firing from, you cannot know where you're firing to. Position error at the launch point rides straight into the missile's own error budget. APL's engineers put it almost that bluntly. Polaris had to know its own position at least as accurately as it was expected to hit its target.
Translation. The world's deadliest weapon system runs on pretty sure we turned left back there. Cozy.
On the 20th of July, 1960, USS George Washington made the first Polaris launch from a submerged submarine. That November the 15th, she left port on history's first deterrent patrol, 66 days submerged by the Navy's own account. And the satellite meant to solve her navigation problem was the one I asked you to remember. Transit 5BN2, which didn't reach orbit until December 1963, roughly 3 years of patrols before the system built to find them worked. And it wasn't standing still on either side of that gap. The following year, by the Navy's own published history, the Polaris A3 more than doubled the missile's range to 2,500 miles and tightened its accuracy to about half a nautical mile. The target was getting smaller and farther away, right as the tool built to find the launch point finally arrived. So what did the boats use in the meantime? Their own inertial system, the Mark II Sins, backed by Loran-C radio navigation, wherever its signal reached. The Navy also looked at a longer-range system, Omega, though it never became the fleet's fix of record. And by most accounts, crews fell back on older tricks too. Star sights through a special periscope, depth soundings checked against the chart. None of it touched the cost that never really went away. A satellite fix could not reach a submarine at depth. Taking one meant coming up to periscope depth and putting an antenna in the air, precisely what a missile submarine spends its entire existence trying not to do.
So the system built to find the world's best hiding boat only worked the instant it stopped hiding. Bold strategy.
Hold the Navy's original ask in your head, because everything from here gets scored against it. A fix several times a day, good to 1/10 of a nautical mile, about 185 meters, from a receiver that transmitted nothing back. That was the ask, not the delivered result. Picture where you'd least want to be waiting for a fix. Somewhere remote and hostile, the top of the world, ice in every direction. That has to be the thin coverage. It's the opposite. Near the poles, a fix every half hour or so. Near the equator, closer to 2 hours. Polar orbits crowd together over the poles and fan apart at the middle, and when the orbit planes drifted, that equatorial gap stretched further still. And no button press got you that fix. You tracked one satellite through its entire pass, 10 to 16 minutes of Doppler, while it crossed 4,000 to 7,000 kilometers of sky. That long baseline is why the fix was accurate. It's also why the ship's own motion became the biggest error in it. One knot of speed wrong cost you about 2/10 of a nautical mile, roughly 400 meters.
A quarter of an hour of listening, and it only works if you already know how fast you're going. That's not a fix, that's a negotiation.
2 clean facts about that fix. It was 2-dimensional only, latitude and longitude, never altitude, and it beat the ionosphere with Gear and Weifenbach's own trick from Sputnik. 2 coherent frequencies, 150 megacycles and 400, bent by different amounts on the way down. Compare the bend and most of that error cancels. Remember that one, it comes back. A dual frequency set holding still put you inside about 25 meters. Roughly 9 in 10 commercial buyers bought the cheaper single frequency set instead. Official predictable accuracy, 500 meters. Same satellites, 20 times the spread, and it came down to what receiver you could afford. And if you know this history, you are about to object that transit did not become GPS. You are right, and that is not the claim, and we will get to exactly what it did become. Here's the turn. Everything that made transit useless for a ship underway, it needed you to hold still, and it took a whole pass for one fix, becomes exactly what you want the moment you actually are still. Stand a receiver on a fixed point, average 50 passes instead of fighting your own motion. And transit stops being a navigation system. It becomes a survey instrument accurate to something like a meter. That accuracy redrew 2 maps. Geodesists used stationary transit receivers to run a completely new survey of Western Europe, tying mismatched national grids to one shared reference. And the same fixed point trick helped position the North Sea line separating Norwegian from Scottish waters. A system built to aim missiles from submarines ended up drawing an oil boundary.
So the same math built to end cities moonlighted drawing an oil border in the North Sea. Somewhere, a cartographer owes the Navy a drink.
The first civilians on the system were oceanographers on research ships in the mid-60s. General release came in 1967. By then, the balance had tipped for good. By the end of 1987, there were an estimated 80,000 commercial transit sets in use. By 1994, the U.S. government counted fewer than 200 military users. Different years, not one snapshot, but however you read them, a system built to aim nuclear weapons had become overwhelmingly a civilian tool. Transit's navigation service itself ended on the 31st of December 1996, closing the books on 32 years of operation, but the satellites kept transmitting. From the 1st of January 1997, the survivors became the Navy Ionospheric Monitoring System, spending retirement measuring the very sky they'd once had to correct for.
Okay, before Mo goes soft on the weapons program, I want it on record that I called this coming. Every documentary does the but actually hear me out bit eventually.
Now, before you decide who the villain is here, the other side has a case, and is stronger than you'd expect.
The easy story is that public science got captured by weapons work. But the same inversion that aimed a missile is the reason a trawler in a storm knows where the rocks are, and the people who built it did not stumble into it by accident. McClure already knew the Navy's problem when he asked the question. And there is a harder argument underneath. A submarine that knows exactly where it is does not need to get closer to be sure. Precision and restraint are not always opposites.
Fine. Point taken. I still think the missile people invented something nice as a weird redemption arc, but I can't argue with a trawler not hitting rocks. Consider the record corrected.
And now the part that runs the other way. In April 1973, the Pentagon ordered the rival satellite navigation programs consolidated into one system. Here's who was actually at the table. APL wanted an upgraded transit. The Naval Research Laboratory was pushing its own system, Tomation. Both of those were Navy. The Air Force had one too, called 621B. And the Army had a fourth, Sea Corps. 3 services, 4 programs, 1 shrinking budget. Consolidation did not mean instant agreement. The first version went in front of the Pentagon's Defense Systems Acquisition Review Council in August 1973, and it was rejected. The council saw exactly one thing: the Air Force's 621B wearing a new name. The revised concept, genuinely joint this time, was approved on the 17th of December, 1973, 24 satellites in 12-hour inclined orbits. That configuration, not the August draft, is the one that flew.
A defense committee that admits its own first draft was just a rebrand? Somebody framed that memo.
So, what actually went into the design that won? The signal came from the Air Force's 621B, a pseudo-random noise ranging code, not transit's Doppler shift. The orbits came from the Navy's Tomation, raised from 8-hour periods to 12. Both programs had proposed flying atomic clocks. Only the Navy had actually flown one. Transit's contribution was quieter. The orbit prediction mathematics and the proof already demonstrated that satellite navigation could be trusted at all. The popular version compresses all of that into one story. Bradford Parkinson, the program's first director, has said he gathered about a dozen people in an empty Pentagon over Labor Day weekend, 1973, and hammered out what GPS would be. Good story, also disputed. Richard Easton, whose father, Roger, ran Tomation at the Naval Research Laboratory, argues that weekend compresses months of real negotiation into one legend, and writes his father's lab out of the credit.
Wait, didn't we already do this? One person, one room, one legendary weekend. We caught that exact move earlier this episode. Twice in 1 hour is not a coincidence, it's a pattern. And I'm just the cat who noticed.
And the consolidation didn't just settle a turf war, it changed the method underneath. Transit read a tone, the rising and falling pitch of a passing satellite, and worked that curve backwards to find you. GPS throws that out. A receiver instead times how long a signal took to arrive, multiplies by the speed of light, and gets a distance to 4 satellites at once. Doppler didn't vanish. It still locks the signal on and still reads your speed. What changed is where your position comes from. Not the pitch, the delay, and the gain is structural. Transit gave you 2 dimensions. GPS gives you 3, altitude included. Transit gave you a fix when a satellite happened to pass. GPS, listening to 4 at once, never stops. 3 of those distances would already pin a single point. 2 range spheres cross in a circle, a third narrows that to 2, and only 1 sits on Earth. So why listen for a 4th? Because the receiver's own clock is cheap. It drifts, and that drift is a 4th unknown hiding inside every measurement. The 4th satellite is what lets a cheap quartz clock behave for the length of a fix like an atomic one.
Hang on, didn't your boss guy already run this bit? 9 unknowns down to 5, just so a satellite could find a submarine. Now, 3 becomes 4, just to keep a cheap clock honest. This family cannot stop counting unknowns.
None of that arrived overnight. The first Block 1 satellite went up on the 22nd of February, 1978, on an Atlas F out of Vandenberg, a developmental prototype, not a working system. 11 Block 1 satellites were launched through 1985, and 1 never made orbit. Everyone went up to test the system. Not one was there to navigate anybody. Here's the story you've probably heard. A tragedy shot GPS loose from the military. The loss of Flight 007 forced Reagan's hand. It's a good story. It isn't this one.
Wait, isn't that the whole story? Tragedy, guilty conscience, here's your GPS? That's the one I know.
On the 1st of September 1983, a Soviet interceptor shot down Korean Airlines Flight 007 after a navigational error carried it into Soviet airspace, killing all 269 aboard. Historians still debate exactly how that error happened. What follows isn't in dispute. 15 days later, on the 16th of September, the White House spoke, not Reagan himself, his deputy press secretary Larry Speaks reading a statement. The United States, he said, was prepared to make GPS available to civilian aircraft once the system became operational. That's an offer, and a narrow one. Nobody declassified anything. A press statement can't. Here's the better story. The civilian channel wasn't wrung from a tragedy. It was written into the blueprint 9 years earlier in the July 1974 Navstar Program Management Plan. You could buy a GPS receiver before Flight 007 was ever hit. Surveyors already were. So why does the myth stick? Because a promise at a podium is visible, and a decision in a filing cabinet is not. We remember the moment we were told, not the one where it was decided. And retire the single moment entirely. Civilian GPS phased in. Surveyors first with six-figure receivers years before that speech. The first handheld for an ordinary person, the Magellan Nav 1000, arrived in 1989 for about $3,000. Continuous worldwide civilian service wasn't guaranteed until December 1993. Full civilian accuracy waited until May 2000. Name the rung, you mean. Here's the strangest fact in this whole story. For a decade, the U.S. government built a lie directly into GPS's own signal. Selective availability worked by corrupting the orbit data every satellite broadcast and by dithering its clock frequency, deliberately, precisely wrong. The system wasn't confused. It was engineered to lie about where and when it was.
So my phone's ancestor was a pathological liar with a government paycheck. Explains a lot.
The capability didn't exist until the Block 2 satellites and the first launch the 14th of February, 1989. Selective availability switched on the following spring, March of 1990. Then months later, it switched back off for the Gulf War because American troops in the desert were carrying civilian receivers the Pentagon had bought off the shelf. To stop lying to its own soldiers, the military had to stop lying to everyone. It went back on in mid-1991 and stayed on nearly a decade. On the 1st of May 2000, President Clinton ordered it switched off, and just after midnight, it was. At a reference receiver, 95% of fixes went from within 45 meters to within 6.3. The promise had been up to 10 times better. It delivered about 7. And here's where this episode corrects its own premise. If you assumed GPS's link to nuclear weapons was about aiming them, you have it backwards. GPS satellites do carry a nuclear payload, just not the one you're picturing. Beginning in the Block 1 era, and on every satellite since, they have flown sensors built to detect a nuclear detonation anywhere on Earth. Detection, not delivery. GPS doesn't aim the bomb, it watches for one. One more inversion because this episode runs on them. Initial operational capability declared the 8th of December 1993 was in substance a promise to civilians. Full operational capability, the military milestone, didn't arrive until 1995. The two flags got planted in the opposite order from the one the myth predicts. So the plain fact still stands. Transit lost. It didn't become GPS and it wasn't merged into it, and it's the ancestor of it, and it kept flying its own missions to the end of 1996. GPS was built on a different bargain, conventional precision weapon delivery, and ending a four-way turf war. Civilians didn't inherit GPS. They were in the blueprints from day one.
So Transit lost the contract and still ended up in everybody's pocket. That's not losing. That's what my accountant would call a very good exit.
Follow one thread all the way down. To beat the ionosphere, Geyer and Weifenbach needed two frequencies. The sky bends a low one more than a high one, so compare the bends and the error mostly cancels. Transit flew that as 150 megacycles and 400. GPS inherited the trick and renamed it L1 and L2, same physics, and still part of how a survey receiver finds a benchmark to the centimeter. That's the real inheritance, not the Doppler. GPS threw that away. A correction for a layer of charged sky worked out on a borrowed tape recorder in 1957 is running right now in the chip in your pocket, and so is the assumption underneath it. The receiver believes what it hears, which is why there are two ways to attack it, and they are not the same failure. Jam it and the receiver hears nothing. It knows instantly it's lost.
Spoof it and it hears something false and believes it. A fake position delivered with total confidence, and no ordinary receiver can tell the difference.
That's the dangerous one. The whole structure still rests on what two men assumed with borrowed gear in a Maryland lab, that the signal is telling you the truth.
Mo won't say it, so I will. Every navigation system we have ever built got used for something its inventors didn't plan. Here's my bet. Dated and on the record. The next one won't be different. And when it happens, blame the cat.
If you want the version of this where the spectrum actually makes sense, how the bands get carved up, who gets to use what, and why any of it holds together, that's what we build at SmartCat. Links in the description, along with everything sourced in this episode. Two men listened to a beat because they were curious, and a machine for ending cities came out of it, and then a machine for finding your way home. Same arithmetic, different question. Check out the next episode where we go deeper into the history hiding inside the signals around you, from smoke to signal.
If this was worth your time, subscribe. There's a lot more of it on the channel. Thanks for watching.